Welcome to section 1.7. We're going to continue our discussion of solutions by talking about an idea known as linear dependence, or also independence, depending on which one you want to focus on. We will talk about this in terms of vectors, talk about it in terms of matrices, and then we'll talk about sets of vectors. So let's talk about linear independence of vectors specifically. So if I have a set of vectors, v1 through vp, so I have a set of vectors in Rn, these are linearly independent if the only linear combination that adds up to the zero vector is the trivial solution, meaning that all of x1 through xp, so all these x's, every one of my x's is zero. If that is the only solution, obviously it is a solution. But if it is the only solution, then we refer to the vector set as being linear independent. Now, linear dependent simply means there exists at least one solution. So it doesn't mean that all of them have to be non-zero. I could have one of them or two of them that are simply non-zero. Now, a linear dependence relationship is any such non-zero set of coefficients, C1 through CP, that gives me that. So a linear dependence solution is essentially a non-zero or non-trivial solution to that thing. So this is how it ties into homogeneous. So let's look at an example. Sorry, I forgot to get rid of those little under slashes. So I have three vectors here, v1, v2, and v3. I want to know if they're linear independent or not. And if not, I want to find their linear dependence relation. So the first question is, are they linear independent or not? In essence, I'm looking at the vector equation, some x1 times v1 plus some x2 times v2 and some x3 times v3 equals a zero vector. Or as a matrix equation, we had this as we put all the 1, 2, 3, 4, 5, 6, 2, 1, 0, all as a matrix. We took all of our vectors. So notice v1 became column 1, v2 became column 2, and v3 became column 3. We did this previously, and now x1, x2, and x3. So this is that ability to go from a vector equation into a matrix. But this matrix equation we can solve by turning it into an augmented matrix. So we have all these different ways to approach. The nice part is the augmented matrix is something we can solve. So go ahead and pause the video and solve that augmented matrix. Go. All right, so if you solve that, here are the row operations that I did. Row 2 minus 2 times row 1 back into row 2. Then I have row 3 minus 3 times row 1 back into row 3. It's looking good. Taking that, I then take row 3 minus 2 times row 2, and I get this this reduced echelon form, which if you will notice, it has a row of all zeros, which one of those columns, this column, does not have a pivot, so it has a free variable. Free variable means there's more than one solution. Boom! We know that this is not linearly independent. If it was linearly independent, there would be a pivot in that column. So we've now answered actually our first question. We know that it is not linearly independent, but that means we now have to find a linear dependence relation. In other words, we need to find one non-trivial solution to this. So we need to continue doing row echelon to get this to get the general form of this thing. So what I would do is I would scale that whole second row by -1/3. So it's really easy to add up and eliminate that 4 in the row 1. Namely, I would then take row 1 minus 4 times row 2. We have this resulting vector, which if you turn that into a system of equations, we get x2 minus 2 times x3 equals 0, x2 plus x3 equals 0, and 0 equals 0. Or, in other words, that x1 equals 2 times x3, x2 is negative x3, and x3 is free. So all we do here is we pick any value for x3 that will give us a non-zero vector. So notice if you pick 0, you would just get the all 0 values. So that doesn't help me. But, by the way, that's almost always what it is. So how about we pick x3 as 1? Well, that would mean that x1 is 2, x2 is negative 1, and x3 is 1. And sure enough, if you take those values and you plug them in using my vectors, 2 times that first vector minus 1 times the second vector plus 1 times the third vector. If you actually did the addition and subtraction, all the arithmetic, you'll find that that is a solution. So that is indeed our independence relationship, is that 2, negative 1, 1. So sometimes this is called the linear independence relation, and sometimes this is what it's called. So most often your text will actually refer to the actual equation with the coefficients. But it is possible that if you go Googling, you will find the latter. It all depends on who's asking the question. All right, come back for my next video as I talk more about linear independence and matrices.